My name is Huagui Yang, and I'm professor in School of Material Science and Engineering at China University of Science and Technology. The research in my group is related to design and synthesis of various functional materials for clean energy and environmental applications. In 2008, we made a breakthrough to synthesize titanium dioxide single crystals with a large percentage of high reactive facet. After this breakthrough, various promising applications have been found for such kind of functional materials. Perspective, we try to combine the theoretical analysis and experimental evidence on unusual properties of Anatase TiO2 single crystals bounded by high reactive facet. Firstly, we highlight recent theoretical studies which focus on the stability, surface properties, as well as the catalytic reactivities of 001 surface of TiO2. Professor Xue Qinggong did a lot of work in this part.
I'm working in the Institute of Industry Catalysis in the East China University of Science and Technology. I'm the co-author of this GPCL perspective. And what we have summarized in this perspective is some theoretical work in the field of TiO2 surfaces from many different many excellent research workers in the DFT community. In the study of TiO2 is how to determine the specific properties of different surfaces of TiO2. Because TiO2 has many polymorphs like anatase, rutile, and brochite, and each crystal also has many different facets. So there are different ways to study the specific properties of different TiO2 surfaces, and what we are doing here now is to use the so-called density functional theory, or DFT, to study the structures and electronic configurations of different TiO2 surfaces.
We will demonstrate to you how a theoretical calculation is taken in a modeling software.
Theoretical work is to do computational simulation, which means we have to build our materials in the computer. So what we have been using in our computational simulation is this very excellent software called Material Studio. And with this software, we can actually do many different things. You can, in fact, do many theoretical calculations at different levels. But we are most often using is to use the so-called visualizer visualizer module in this software to do computational simulation to build our materials. For example, as you may be familiar with, we can build the two different surfaces of anatase. We can actually using the DFT code, like what we are using is WASP and PWSCF to optimize the structures. So here we show in this slide is optimize the 001 surface of Anatase TiO2. And after we get the optimized structure of TiO2 Anatase 001, we can then do some simulation of the adsorption of molecules. For example, we can model the physical adsorption of formic acid molecule on this Anatase TiO2 001. And here is a multiple expansion of the surface cells. And we can see the molecular formic acid adsorbs on the surface physically. And by doing calculation, we can then estimate the adsorption energies. Also, we can build some other different surfaces. For example, for Anatase TiO2 001, we know that it can undergo some reconstruction to form a 4x1 reconstruct surface, which we can also model with this software. So this is actually a very powerful software.
The addition result of TiO2 bounded by high reactive facet is also quite exciting. For example, it can be used as an excellent photocatalyst to decompose some organic compound. The application as anode materials for lithium-ion batteries, the corresponding irritable capacity loss of this TiO2 is only about 10.7%, which is much lower than that of benchmark TiO2. It should be noted that all these application studies, such as the water splitting or dye synthesized cells, are still in its early stage. More systematic work are needed in the future to clarify its industrial importance. The unusual properties of Anatase TiO2 bounded by high reactive facets have been found theoretically and experimentally. Some challenges still exist. For example, the photocatalytic properties need to be enhanced further, especially in the visible light region. Also, the chemical and thermal stability are also need to be studied. Design and synthesis advanced crystalline materials. I believe one day we can find a practical solution for the energy and environmental issues in the future. I welcome you to visit our lab sometime later on, and I'm looking forward to having the chance to cooperate with you on some of these topics. Thank you for your time.